Hello everyone, welcome to 1103 Business Mathematics 1. I am Renovia Simanjuntak and today we will learn about set on and counting, which is taken from chapter 6 of TAN textbook. So here we will learn something which is a bit different with what we have learned before. So before we learned mostly part of calculus, but now we will learn part of what we call combinatorics. Okay, so the first subchapter will be about sets and operations in set. And of course, we should start with the definition of a set. So what is a set? A set is a well-defined collection of objects. So here, of course, a set contains objects. But it has to be well-defined. Or in other words, we know which objects are in a set and which are not. Okay, so these objects of a set are usually called the elements of a set. And then we usually use lowercase to denote those elements. While the uppercase letters we use to denote the sets themselves. So if we have an element of a set A, we write in this notation. And we can say either belongs to A or an element of A. On the other hand, if we have an element which does not belong to the set A, we write it this way, and we read A does not belong to A. So let's see this example. We have the set consists of 1, 2, 3, and 4, and 5. And then of course 3 is an element of A, or 3 belongs to A, but 6 does not belong to A. Okay, so the notation that we used before is what we call the rooster notation. So if we have the set A, which consists of the first 3 letters of the alphabet, and then we can use this notation, A is equal to A, B, and C. The second example, if we have B, which consists of all letters of the alphabet, we can write it down as this one. B is equal to A, B, C, and so on up to Z. But we can also write the set B here by using what we call the set builder notation. So this is how we write in set builder notation. So we have B equal to X, such that, so we have this line here, which we usually read as such that X is a letter of the English alphabet. Okay, so these are the two ways to write the notation of a set. Okay, so if we have two sets, how do we decide whether these two sets are equal? So it happens in and if and only if those two sets have exactly the same elements. But if we have every element of a set A is also an element of a set B, we say that A is a subset of B. And then it is written with this notation. Another important notation, if we have a set which has no elements, it will be called an empty set, and it is denoted by this notation. So let's see these two examples. So we have 3 sets, A, B, and C. And if we are asked which sets are equal, remember, 2 sets are equal if they have exactly the same elements. So you can see, even though it is written in different order, but the elements of set A and the elements of set B are exactly the same. In that case, we can write A is equal to B. What about this question? Yeah, which set is a subset of another set? Yeah. So we say a set is a subset of another set when every element of the set is also an element of the second set. Yep. And of course, if we consider A, it will be a subset of itself. Yeah, because every element of A is also an element of A. So we have here A should be subset of A. Yeah. What about A and B? Yes, every element of A is also every element of B, so we can write that A is a subset of B. What about B? Yeah, B, of course, similar to A, is also a subset of B, and B is also a subset of A, yeah, because every element of B is an element of A. And what about C? Yeah, C is, of course, a subset of C itself. It is also a subset of A, and it is also a subset of B. Yeah, you can see every element, A, E, I, and O, are included in both A and B. Okay. What about the empty set now? Yeah. The empty set is, of course, will be a subset of every other set. Yeah, because no elements, yeah, will be part of any sets, right? Okay. So, but it is not an answer to this question here because the question is which set is a subset of another set. So we have to include A, B, and C only. Okay. So now we have another set which is A, yeah, A, which elements are A, B, and C, and then we have to list all the subsets. And as I said before, of course, empty set is a subset. And then if we list all the subsets with only one element, so we have A, we have B, and then we have C. And then we can also list all the subsets with exactly two elements, AB, AC, and BC. And then we can also have A, because A is also a subset of A. So these are all the subsets of the set A. Now to better visualize sets and its elements, yeah, especially if we have more than one set, we usually use what we call the Venn diagram. Yeah, and in Venn diagram, we usually have what we call the universal set, which is what? Which is the set of all elements in interest of the discussion. Yeah, so it is the largest set because it contains all the elements under considerations and also contains or also has all the sets under consideration as its subsets. Okay, so this is some example of the Venn diagram. Yeah, the first one is if we have A equal to B. Yeah, so here the white one, yeah, and everything actually is the universal set. And then we have A equal to B, yeah, is the set here, yeah, which is a subset of the universal set. Now we have what we call a proper subset, yeah. So remember here, you can see that there is no equality sign, which means A is a subset of B, but A is not equal to B, yeah. So here we see every element of A is inside B, yeah, but A is not equal to B, yeah, and then both of them is also subsets of the universal set. And in here we have a Venn diagram of where A is not subset of B and B is not a subset of A. Yeah, so you can see here A is not a subset of B. In this diagram also A is not a subset of B, and the other way around, B is not also is also not a subset of B. Of A, I'm sorry. Okay, so let's see operations of set. Yeah, so if we have two sets, we have the first operation, which we call union, and the notation is this one. And what is that? That is the set of L elements belongs to either A or B or both. Yeah, or if we use the set defining notation, it looks like that. Okay, and here we have the Venn diagram. So the element is either in A or in B or in both A and B. The second operation is about intersection, yeah, written as this notation, yeah, and this is the set of elements common to the sets A and B. So it has to be in both sets A and B. Yeah, yeah. The Venn diagram is this one. Yeah, so it is inside both. The elements is in both sets A and B. Yeah, and then if we have an empty set intersection, so if the intersection between A and B is an empty set, then we can say that A and B are disjoint. Yeah, or in other words, A and B do not have element in common. Okay, and then the last operations that we will learn here is the complement of A. Yeah, we denote by AC here, and this is the set of all elements in U which are not in A. Yeah, so the Venn diagram is something like this. We have all elements in U which are not in A. Okay, so based on the definition of complement, we can have these properties of complement. Yeah, the first one, if we take complement of the universal set, it will be just the empty set, right? Yeah, because the universal set already contains everything. And if we take the complement of an empty set, it will be equal to the universal set. And then if we take complement of a complement, it will go back to the original set. Yeah. And then if we take union of A and its complement, it will be equal to the universal set, of course. But if we take the intersection of A and its complement, it will be equal to the empty set, because this intersection doesn't have a common element. Okay, and then all the set operations that we learned before have several properties. Yeah, this first one is it is commutative. Yeah, for both union and also intersection. Yeah, so you can see that the union of A and B is the same with the union of B and A, and it is also similar for intersection. And it is also have an associative property, yeah, for both union and intersection. Yeah, so it doesn't matter which, if you have three sets, it doesn't matter if you take the first two union first or the last two union, you will have the same result. Yeah, yeah, so if you take A union B first and then take union with C, it will be the same with if you take B union C first and then take union with A, sorry. And then very similar, we also have associative law for intersection. And the last property will be about distributive for both union and intersection. Yeah, so if we take A union of B intersection C, yeah, it will be equal to A union B intersection A union C. Yeah, and we have a very similar property for intersection. Okay, so let's see one example. So let's U be the set of all cars in the Elder slot. Yeah, and we have A is the set of cars equipped with an XM radio. B is the set of car equipped with a moonroof, and C is the set of car equipped with side airbags. So now if you want to see the set of cars with at least one of the given options, so it means that the car is an element of either A, B, or C, or maybe two of them, or maybe all of them. Yeah, because this is only at least one. So what does it mean? It means this set of cars will be just A, Union B, Union C. Okay? And then we have another question. The set of cars with exactly one of the given option. So it only has radio, yeah, or it only has moonroof, yeah, or airbags, yeah. So how do we write this expression in terms of A, B, and C? Yeah, you can think about that. And also this last question, yeah, about the set of cars with Sirius radio and side airbags, but no moonroof. Yeah. So how do we express this in terms A and B and C? Okay, just think about it and try to find the answer. Okay, so that's all about the first subchapter. Thank you for your attention. And then see you again in the next video on the next subchapter. Goodbye.